Moment just so I could see everybody. And yeah, this looks kind of all right. Hi, everybody. And so, welcome everybody to our April 30th colloquium in the Department of Physics, Astronomy, and Geosciences. My name is Christian Reddy. I'm a lecturer at Towson University where I teach astronomy and astrophysics. I'm also director of the planetarium. And I also, of course, have a YouTube channel called Launchpad Astronomy, which some folks are very kindly joining us from as far away as Vancouver, Australia, Sweden, and wow, how cool is that? So we're going global today, and that's kind of good because we are talking today with our guest, Dr. Brian Keating, who is the Chancellor's Distinguished Professor of Physics at the Center for Astrophysics and Space Sciences in the Department of Physics at the University of California, San Diego. And he's a public speaker, an inventor, and an expert in the study of the universe's oldest light, which is a cosmic microwave background. And what he's been doing is using it to not just learn about the origin and evolution of the universe, but now he's starting to come to some very interesting areas which may allow us to reevaluate some of the very foundations of physics itself. And so, it gives me great pleasure to introduce to. Oh, and by the way, I should also say he is also, I forgot, a writer and author of Losing the Nobel Prize, a wonderful book about his work with the Bicep 2 collaboration. And he's also the host of the Into the Impossible podcast, which is available on Apple Podcasts and right here on YouTube at Dr. Brian Keating. So, please join me in welcoming Brian Keating to today's colloquium. Hello, Brian, and let me go ahead and spotlight you. Hello, Brian, and welcome to Towson University.
Hello, Towsonites, Towsonians. I don't know. How do you say it? I know a good deal about you guys, thanks to Christian. And it's great to be there, be here, be virtual with you all. And I'm going to try to share my screen. I have been doing that with some degree of success in the last few months. I've been teaching cosmology to my brilliant undergrads, some of whom may be on this call or listening in, at least on YouTube, that version of it. And it's a great treat to be here to give a virtual colloquium. So I'm going to, let's see, I'm going to share screen. I'm going to share my
recording in progress.
Oh, good. The FBI warning has been established. Good. And I'll share my second desktop there. And then Christian, you will be in charge of telling me if you can see the slide that says Losing the Nobel Prize.
I can, in fact, see that slide, yes.
Wonderful. Well, as I said, it's a great pleasure to be here. And I am coming to you all the way from Southern California, beautiful, sunny San Diego, where I have hosted visitors from Towson in the past. And I hope to maybe use this as an opportunity to recruit students to consider UC San Diego for the future, and wherever your graduate school ambitions may take you. I'm hoping you will consider perhaps coming from Towson all the way to San Diego. I think we're almost as far apart as can be possible and still remain in the continental United States. Although I do have a student, Joseph Seibert, who came all the way from Bowdoin, which is in northeastern Maine, somewhere up there. And he came pretty darn far, at least within the United States. I have students from Canada as well. But anyway, we are going to talk today about an exciting new field of development, which is as old as the universe itself, namely the cosmic microwave background radiation. And I'm going to hope to take folks on a little bit of a guided tour of the universe using my book, Losing the Nobel Prize, as Christian nicely plugged. He gets 5% of every book sold. No, he doesn't. Not yet, at least. But I hope that it will convince you to at least find the story of our cosmic origins as inexplicably delicious and delightful as I do, and really surprisingly, to discover that our universe's fate and its origin are intimately linked to the properties of the humblest substance on Earth, which is dust, and perhaps the humblest substance in the cosmos, which is dust. So the subtitle of this talk is, I'm calling it Dust to Dust. And the reasons why will become clear as we go along. And I will highlight some discoveries that are going on in my collaboration, the Simons Observatory, and in other collaborations around the world and around the planet, in fact. First of all, 2 calls to action. You all have your phones with you. If you take out your camera and point your camera at the top and then bottom little QR codes, you'll be instantly teleported and transported into my universe, which is consisting of outside of teaching and research, consists of producing public outreach inspired in part by Christian, to do a little bit of my part to give back to the universe in such a way as to reward the people that pay our salaries. You guys out there watching on YouTube at least are responsible for paying the salaries of any public scientist who's taken funding from the National Science Foundation or from NASA. And I believe it's a moral obligation, as I always say, that we give back to those of you out there who pay our salary. So wherever you're watching this, unless you're watching it on your phone, that would be kind of hard to do. But if you're watching on a computer, take a picture with your phone, the top and the bottom, and you will immediately become a part of my universe. And I hope to share with you conversations with the most brilliant minds in the universe, including 9 Nobel Prize winners, a Pulitzer Prize winner, 3 billionaires, and all of those together in the form of Christian Reddy when he came on the show. No, I don't know if Christian is a billionaire yet, but he tells me the first billion is the hardest. So please do that. And I want to start with, as I say, Dust will make a not insignificant contribution to this talk, as it does to every phenomenon in the universe, more or less. There's a meme on scientific Twitter whenever they talk about some new miracle drug that cures cancer, and or some deadly new finding about coffee, which reminds me to have a swig of my Irish coffee. It's 12 o'clock there, so I can have Irish coffee here, even though it's 9 a.m. No, it's not Irish coffee. It's just all regular coffee. But nevertheless, people in the biological corridors of Twitter and elsewhere will talk about these findings, and then in the subprint it'll say in mice. And the thing is, you should always add in mice, or clarify that these findings about deadly new effects of coffee or wonderful new results from some promising cancer drug usually come from mice, and that's fine. But I'm on a campaign to get people to be more aware that most of the discoveries that we see nowadays, dust plays some role within it. And it always bothered me when I was a kid. I'd buy these books by people who have lately become guests on my podcast, such as Sir Roger Penrose, or Frank Wilczek, or Sheldon Glashow, all of whom I've had on my podcast, and many others. And you'd get their hardcover books, and immediately the dust jacket would fall off. I was like, well, why do we need a dust jacket? Like how much dust is raining down onto people's books? Like, why do we need to have a dust jacket? And in fact, I came to realize that the dust jacket is perhaps the most important part of the book, because it's the only way, in fact, in my book, that you can actually get a sampling, an actual physical embodiment of the villain of the book, Losing the Nobel Prize. So it's gone from trash to treasure, as I believe it does throughout all of astronomy and cosmology. This notion that dust is ubiquitous and underappreciated. And it even played a role in the very first optical astronomer to ever use a telescope in the history of humanity. And that, of course, is my hero, and I know many of yours as well, and that's Galileo Galilei. And Galileo Galilei, I have all my heroes. I have finger puppets for all my heroes. So here's one here. And sometimes I give them away on the YouTube channel, so make sure you subscribe, as I said. And Galileo used a telescope. He wasn't the first person to use a telescope, but he used it for the first time to point at the heavens and derive conclusions and test hypotheses about the nature of space, time, and the universe, and even the laws of physics itself. And for that, his reputation would be firmly cemented if that was all he did. But of course, he did much, much more. In fact, 411 years ago, last month, effectively, he published on March 13th, he published this book, self-published book, which I have been tempted to do on occasion, again, without peer review, which should be pointed out, Sidereus Nuncius, the sidereal messenger of Galileo Galilei, or the starry messenger. The starry messenger is meant to communicate the discoveries. It was really a a kind of a coming out party for the telescope. No one had ever used a telescope astronomically. At least no one had reported their findings. People obviously had probably looked at things through the telescope, which Galileo called the perspective tube, perspiculum, and that perspiculum gave him a new perspective on the heavens, which some of which is sketched in these illustrations shown in the upper left, shown from January 1610, where he observed these 2 or 3 bright stars, eventually 4 bright stars, accompanying Jupiter. And he had the brilliance. I would have said, okay, well, Jupiter's just moving, and there are some stars nearby, and we know that Jupiter's a planet, and planet means wanderer in Greek, and therefore it's just wandering, and there are some background stars. No, Galileo was much more brilliant than I could ever be, and he instead realized he was looking at a small solar system edge on. It was really phenomenal to think about that. The instantaneous elucidation that what he was seeing was not just some stars in the background, but there was a miniature solar system of stars or tiny accompanying stars, as he called them, and they were orbiting around Jupiter. And he made enough observations to at least determine to himself, to his own satisfaction, that these objects were, in fact, comprising a tiny solar system in miniature, although he realized Jupiter was quite large and quite far away. And then he went on to observe other phenomena, such as the structure of the moon's surface and the composition of it, which had been thought to be perfectly smooth and uniform. And in fact, he measured mountains and he estimated the heights of the mountains on the moon, which were thought not to exist. And he drew images in his own freehand form, shown in these beautiful drawings. And today, a good copy of the Sidereus Nuncius that's authentic will cost you about $2 million, if you can even find one. There's only a couple hundred left. And in this book, he really lays out, again, in self-published form, the structure of the cosmos that he would later use to justify the Copernican model that the Earth is no longer the center of the solar system. So I call the telescope the shortest lever ever devised that literally moved the Earth, not just figuratively, but it literally moved the Earth from the place of being central in the cosmic pantheon of centrality. A few months later, he did what all professors would do. He took it and tried to make some scratch from it. He tried to make some money, some moolah from this, some merch. And he knew he couldn't really make enough copies of the telescope to satisfy demand. And Sidereus Nuncius made him famous around the world. So instead, he said, it's easier to make digital copies, or, at least not digital copies, printed copies of the manual for a device rather than replicate the device itself. And besides, he had a monopoly. He was the only one that could make the powerful magnification necessary to reveal those features, which he then showed to the Venetian Senate, the Doge, and others who would become his patron. And he did so to convince them of the military benefit of this device, because here in the Campanile and the towers in San Marco Piazza, he could show that you could see a boat coming 2 days before you could see it from shoreline, or even from the tower itself. You could see it through the telescope. And so it provided a tremendous military advantage. And as my guest 2 weeks ago, Neil deGrasse Tyson, pointed out, for a long time, astronomers have been what he calls an accessory to war, helping in the effective practice of military campaigns, strategic or actually tactically, with military governments and militaries around the world. And Galileo is not by no means the first to do so. So he sold it. He got actually tenure from doing so. He didn't get tons of money, although he did effectively double his salary, which was basically salary plus startup. So that's pretty good for us professors. But again, he didn't want to give away the telescope, because that would be like giving away, the atom bomb secrets, right after we discovered it, or the laser secrets, more pertinent for Towson, say. So instead, he gave away the books, and he didn't give them away, but he did what we all do as authors. He went on a book tour. He never really left the nation of what would later be known as Italy. It wasn't a nation at that time, and he developed quite a good deal of confidence, like his fellow best-selling author shown here had. And in fact, he had so much confidence that he decided the prior injunction against teaching the Copernican theory, which he promulgated in Sidereus Nuncius, he decided that didn't apply to him anymore. And in fact, he wrote his next book, or his next major book. He actually wrote 6 or 7 books between 1610 and 1632 when the dialogue came out. The dialogue, I don't speak much Latin. I don't speak much Italian. But the Siderius Nuncius is written in Latin. That was okay. That was kosher, so to speak. The Pope had allowed him to study the Copernican theory, which meant doing it in the language of academicians, which was the language of Latin, which the populace didn't understand. And that was fine because it wouldn't cause any kind of uproar or uprising. And there was no problem really with doing so. However, he sort of forgot about that or tested the limits based on his renown that he achieved. And he published this book, The Dialogue, in Italian. And you see he put his title underneath there. So his name, Galileo Galilei Linceo. Linceo means Order of the Lynx. And it was kind of like winning a Nobel Prize back then. You were like in the pantheon of heroes of Italian scientific society and otherwise if you were a member of the Lynxes. So it was like putting Nobel Prize winner on your book. But anyway, he dedicates it to the Grand Duke of Tuscany. And there's so much richness in this book that when I went back to read it again, I was reading it for a video I did not too long ago about how the dialogue influenced scientific writing most effectively more than any other scientific book, even according to Albert Einstein, who wrote the foreword to the modern translation of the dialogue into English by Stillman Drake, who used to be at the University of California as well. And Einstein said it's the greatest book ever written, basically, in scientific history, in terms of popular science expositories. And I said, wow, this is great, but it's 500 pages long. I got a bunch of kids. I got 44 undergraduates, 4 graduates. Do I really have time, to read? No, let me go download the Audible copy of it. That's what I do with most of my guests who are authors who come on the Into the Impossible podcast. And let me go get the Audible. Wait a second, it doesn't exist. The audiobook for this does not exist. In fact, none of Galileo's audiobooks exist until now. So I decided that since it didn't exist and I wanted it, I would do it. I would make the first ever audiobook of the Galileo's dialogue. And if you subscribe, as I hope you will, to my newsletter, you'll get the first kind of draft of it, which I am doing not solo. The dialogue is just that. It's a trialogue between 3 characters. There's one named Salviati, the savior, and he is going to be played in the upcoming Keating production of Galileo's dialogue by none other than Carlo Rovelli, who is one of the most famous physicists in the world today. And he's also happens to be Italian. And the dedication, the prologue, the foreword to the dialogue we are doing is by Fabiola Giannati. So she's going to read the foreword that Galileo dedicated it to the Grand Duke of Tuscany. And I have some other Italians and also Jim Gates, who's the president of the American Physical Society. He's reading one of the forewords. And then Frank Wilczek is reading Einstein's foreword in the original German. So it's going to be a wonderful thing. Look for that. Again, you'll get first dibs on it when you subscribe to my newsletter. So what did it do? Well, it ushered in the heliocentric notion that the sun is the center of the cosmos, for which Copernicus had very little evidence to go on in the late 1400s or late 1500s, when the Copernican De Revolutionists came out in the 1500s. He didn't really have that much to go on, and yet he did conjecture correctly, as Galileo would further ratify, but not prove. So Galileo, by establishing that Jupiter had moons, he did not prove that Copernicus was right. He just motivated the fact that the Earth, being the singular center of our solar system, was wrong. And that's a very important aspect of this proof in scientific philosophy. It's actually not possible to prove almost anything in science in the way that a mathematician would be comfortable with doing so. In return, we get to do things that mathematicians can't do. Whenever I have a mathematician on, like Roger Penrose, I'll say, give me a triangle. Hand me a triangle, please. How much does a triangle weigh? These are purely fictitious things that don't exist in reality. Of course, they can prove things. We cannot prove things, but we can disprove other things. And what Galileo disproved was that the Earth was the center of the solar system, which had prevailed for thousands of years. And you'd think he would be celebrated. Of course, he wasn't. He was brought before the Holy Office, which is a euphemism, much the same way that, Internal Revenue Service is a euphemism. I mean, they tax us. They don't like generate revenue, right? But anyway, he was brought before the Pope, who had been his friend, Pope Urban VIII, in red over there. There's a guy with a sword and a stick, conquistador-looking dude over there, and he was forced to abjure and detest his previous claim that the Earth was not the center of the solar system. And much has been written about this. I do discuss the affair in my book, and I also put to lie the claim that he was tortured for science, that he was imprisoned, shackled in a dungeon, and thrown into jail. In fact, this is where he spent the last few years of his life. It's so nice that it's a tourist attraction, not only for the fact that Galileo spent the last 9 years of his life there, but because it overlooks the Duomo of Florence. This is in the hills of Tuscany, has olive trees, as you can see there. And we had a conference there in 2015 to celebrate 100 years of Einsteinian relativity, but also harken back to Galileo, the father of relativity. And so we had a conference there, and it's a lovely, sumptuous 20-room villa. It's quite wonderful. And actually, it was very close to his daughter, who is in a nunnery not too far away from, about 1 kilometer away from where these pictures are taken. So he wasn't tortured. He wasn't thrown in a dungeon. He actually wrote another book after this called The Discorsi, which is also a dialogue with the three characters. Oh, by the way, the character in the dialogue who voices the popes and the Catholic Church's arguments of Aristotle, of Ptolemy, his name is translated into the simpleton. So that's not, for one of the smartest men who ever lived, Galileo was surely capable of many blunders in his own right. And in the middle here, with the guy taking a selfie, kind of in the middle there, that's Lucio Piccirillo. He's one of the three co-authors. He's reading the part of Simplicio in the dialogue book, along with me and Carlo Rovelli. So what did Galileo show? Well, he showed out to the realm of the stars in the Milky Way. And he thought he understood the nature of starlight in the Milky Way, that any glow in the Milky Way could be attributed to stars if he could resolve them, if he had a big enough telescope. Of course, he didn't have a big enough telescope to resolve all the glowing nebulosity in, say, the Pleiades, which is shown here. The Pleiades cannot be resolved into individual stars, besides the famous six sisters, the Subaru, the Pleiades. And in fact, the glow cannot be resolved because it's not individual discrete stars. It's actually dust. But Galileo said, no, I've revealed with my telescope the nature that all the glow of the Milky Way is actually due to stars. And if I had a big enough telescope, I could resolve them. So dust actually flummoxed the world's first observational astronomer and tricked him into thinking what he was seeing was actually all there was. Going beyond that, Hubble went out even further. This is now fast forwarding 300 years. A lot happened, obviously, in those 300 years. But as I describe in Losing the Nobel Prize, there are sort of 5 major episodes in cosmic history. I call them these great debates over either the presence, the centrality of the Earth, the centrality of the sun, the centrality of the Milky Way galaxy, the centrality of our universe, and how each one of these different episodes has had a huge influence played upon it by this humble substance, namely dust. And in fact, one of the reasons that Hubble overestimated it, the distance to the Andromeda Nebula, which was then discovered to be a galaxy, an island universe in its own right, was partially due to the reddening caused by dust and the fact that photographic plates are less sensitive to red light than to blue light or bluer light, which is why you used to be able to go into a dark room, and that was actually red lighting inside of a dark room because it wouldn't expose the photographic emulsion. Namely, the photographs are less sensitive. Therefore, they wouldn't detect things that had been reddened, and therefore they wouldn't detect things that had excess dust contamination. So dust impacted it, and it caused a huge embarrassment for cosmology for decades. Because although Hubble was a genius and did tremendous work, along with extending the work of Henrietta Swan-Leavitt and Vesto Slipher, who are indispensable to what he did, nevertheless, his estimation of the Hubble constant at that time was 7 times too big. And as you may know, the age of the universe is proportional to 1 over the Hubble constant. So if the Hubble constant was 7 times too big, then the age of the universe is 7 times lower than it actually is. And we actually know the universe is 14 billion years old today. Namely, Hubble thought the universe was 2 billion years old. at a time when the age of the Earth was known to be 3 billion years old. So in my book, I talk about how embarrassing that was for cosmology to sort of be like telling somebody that your parents are younger than you. It was embarrassing that the Earth was older than the universe that supposedly contained it. Here's an image by the Spitzer Space Telescope, and it shows the predominant effect of dust in the universe. And of course, going farther out, we see cosmic wallpaper, the Hubble Ultra Deep Field. Every image here, with the exception of one star, is a galaxy. There's thousands and thousands of galaxies in this one image, about 100 billion over the entire observable universe that we can see in the intervening 13.8 billion years since the Big Bang. And then fast forwarding 30 something years since Hubble, 40 years since the observations I showed from Edwin Hubble, Penzias and Wilson discovered this uniform glow of microwaves from their telescopic perch in Holmdel, New Jersey, not far from Towson. And along the way, 13 years later, won this particular prize. I ventured back there with a copy of my book to show that even if you lose the Nobel Prize, it's still an amazing place to go. And I think it's sort of a cathedral to science. And it's a part of the National Historic Landmarks, not just in science, not just in the American Physical Society, but it's a national historic landmark. And it's under some threat. There are plans to maybe move it or decommission it. And I hope that it will remain where it is. It's a wonderful facility, and I hope that people will visit it while you still can. So going further, even still 30 years after Penzias and Wilson's discovery, there was discovery that the universe not only had a uniform glow of microwaves, but that uniform glow ain't so uniform. It had tiny fluctuations in it. The question being, at the age at which the CMB was produced, namely 400,000 years after the Big Bang, what was around back then to cause tiny little fluctuations in the amount of heat energy owing to its earlier asymmetry in space and time? And the best model that we have currently for such a phenomenon is known as inflation. Inflation posits that the early universe was actually suffused with a quantum field. And like all quantum fields, they cannot resist having tiny perturbations, tiny fluctuations that are present at extremely early times, namely at times comparable to, say, 100 or 1,000 Planck times, the smallest increment of time that physicists really can process. And the extrapolation from when the age of the universe was about 10 trillion seconds old, which is 400,000 years old, to 10 to the minus 37 seconds is an order of 50 orders of magnitude. And now imagine trying to do that in the biological domain. Now, this is not a rat or a mouse. This is a human blastocyst. A human blastocyst is the byproduct of the conception process, shall we say. Sometimes I say it's like your own personal Big Bang, or when your parents had a special kind of Big Bang, but I'm not going to say that today. And now trying to imagine, what did that blastocyst become? What were the initial conditions of such a blastocyst that led it to become the person that it became today, which is this lovely woman, the most popular person in America, I'm told. That's Oprah Winfrey. Well, 2 billion seconds compared to 1,000 seconds is only an extrapolation of 2 times 10 to the 6th. It's pitiful compared to 1 times 10 to the 50th. It's just unbelievably difficult to do what we're trying to do, and yet we're trying to do it. We're trying to take a telescope on Earth and peer back past the planets, past the Pleiades, past the nebula, the other objects, the globular clusters and stuff in our Milky Way galaxy, into the realm of the Hubble Deep Field, beyond that to the realm of the cosmic microwave background. And then we can no longer use light, because light is completely absorbed and then re-emitted at the so-called surface of last scattering that is representative of the time when the CMB first formed. It's like trying to look through a mirror. A mirror has electrons, and it has sort of the same behavior as a plasma, and that plasmas are very efficient scatterers of light, or reflectors of light, as a mirror is. But if you're, say, looking at a mirror, you could hear something going on in the other room. If there was, say, a loud noise or a party or something, you can hear it. In other words, you can use another type of sensation to go farther back in space, and therefore go back in time even further, perhaps to that Planck era, perhaps to that 10 to the minus 37th era. And in doing so, we're following a tradition not unlike that of Galileo, using a small refracting telescope. In this case, this is the BICEP 2 telescope, which is the successor to the BICEP 1 telescope that I created with my colleague Andrew Lang and Jamie Bach at Caltech back in 2001. It's the 20th anniversary of that. We were funded in part by David Baltimore. He's got, at least a namesake connection to Maryland. And David was president of Caltech at the time, and he gave us $1 million, and we ended up getting 9 more. And we built the BICEP 1 telescope and later the BICEP 2 telescope, which is a refracting telescope using ultra-sensitive superconducting detectors, the most sensitive detectors of their kind. And we use it not to make images through glass lenses like Galileo, but using just very purified polyethylene like milk jugs are made of. And we expose them, as I say, not on our retinas as Galileo's doing on the left, but on these arrays of, it looks like a CCD camera, except instead of a megapixel or 40 megapixels, as is de rigueur nowadays, there's only 256 spatial pixels there, 4 16 by 16 arrays. Each one, though, has 2 polarization sensitivities. And each one, unlike your iPhone, which will void its warranty, I'm told, can be cooled down to 0.25 degrees above absolute zero. It does so with a helium isotope called helium-3. And this whole instrument is about 5 to 6 feet long, and it's packaged and put into a mount, an alt-as mount. It's like a Dobsonian telescope for those of you listening on Christian Reddy's wonderful Launchpad Astronomy. And that is this BICEP 2 telescope is the world's coldest telescope. It's actually colder than the telescope that was in space. The Planck telescope can achieve colder temperatures than the CMB itself, rather, which is 454 degrees below 0 Fahrenheit for those of you in the United States. It's quite compact, even though 3 meters sounds pretty big, but it's pretty small. The whole telescope, its aperture. We amateur astronomers love to talk about getting bigger and bigger telescopes. This telescope's only 12 inches aperture in diameter. It's not very big compared to some amateurs have telescopes twice as big. And yet it can do remarkable things if put in the right location. So for us, I would be much more relieved, as would be my kids and my wife, if it could just be stationed here in San Diego. But unfortunately, it couldn't be. It had to go to the South Pole or some high mountaintop because water vapor in the Earth's atmosphere absorbs microwaves. And so we took it to the South Pole because the United States owns the South Pole, so to speak, because we operate the Amundsen Scott South Pole Research Station. It's the very bottom of the world, the axis on which the Earth is spinning. It's also about 9,300 feet above sea level. It's extremely cold, extremely dry, and therefore there are fewer water molecules in the atmosphere above the South Pole to absorb photons preciously traveling since the origin of time and space itself, potentially. So Antarctica, the continent, was not reached, in fact, and thought maybe not even to exist for thousands of years. And it wasn't known where the South Pole was or what the nature of the South Pole was until it was reached 109 years ago, 110 years ago, by these 2 teams. One, the top Norwegian team led by Amundsen, bottom team led by Robert Falcon Scott. They used competing technologies, we would say. Technology at the top, very friendly, man's best friend. Also, man's favorite meal and the South Pole, apparently, which is why the Brits would refuse to eat their dogs, and they decided they would do it themselves. And that actually cost them their lives, many historians think, because they had to bring more people to carry the weight of the sleds. They didn't have food when they got to the South Pole in the form of their transportation animals at 9,000 feet above sea level. And because there were more people, they had to bring more food, more fuel, more supplies, and it just kind of geometrically compounded. They got there 3 weeks after the Norwegian team and witnessed probably the most depressing thing in history, which was the sight of a Norwegian flag on the horizon, which they then realized meant that they were the second team to reach the South Pole. Again, they missed it by 3 weeks. And that would be like Neil Armstrong and Buzz Aldrin and the late, great Michael Collins, who passed away this week. When Neil and Buzz, imagine them stepping out of the Eagle and they land on a Russian flag. That would have been pretty disappointing, pretty depressing. But at least they didn't die. But the British team did, and they could go back home. But it would be very disappointing for national morale, which the South Pole was sort of the moon race of the early 1900s. Today, the South Pole is still extremely dangerous as this grainy Zapruder-like image that I shot will reveal. So here are some of the denizens of the South Pole. No, these aren't at the South Pole. There are penguins at the South Pole, but they're in the gift shop, and then they're stuffed. And I always bring a couple back for my kids. But maybe penguins just are like, physics faculty. They just don't get along with each other. Maybe they're fine with other creatures. So that emboldened me to get close to one. And this grainy footage shows that you should avoid that as well at all costs. So you have to prove that you survived this dangerous voyage. There I am at the South Pole, taking a picture, sending it to my wife. She said, who cares, when are you coming back? But nevertheless, we ended up making a great discovery and a huge announcement. We discovered evidence that we claimed was the first direct evidence for the inflationary quantum mechanical origin of perturbations in the early universe that led to those anisotropies, those fluctuations in the microwave background, in this beach ball behind me right there, that then propagated and would form throughout space and time enormous reservoirs of dark energy, of dark matter, of ordinary matter, of planets, people, and so forth. And that was called B-mode polarization, and it made a not insignificant splash. The day we came out with this result on St. Patrick's Day, 2014, it's hard to believe it's been over 7 years. There was a video produced very slickly by my colleagues and friends at Stanford University. There's Andre Linde in the back right there. He's one of the fathers of new inflation, along with others that I describe in Losing the Nobel Prize. And it was covered around the world. There's a Nobel laureate in the front row down below, John Mather, who was a guest on my podcast a couple of weeks ago. It was on CNN. It was on the most important newspaper in the world, the San Diego Union Tribune. And there I am at the at the middle left there. I like this headline in The Economist because it sounds like just like some dude is looking up and he sees the beginning of the universe. But in fact, we had seen what we thought and what everybody thought was unequivocal evidence for the origin of the universe via this quantum process known as inflation, sure to garner not just recognition for this discovery. Some called it, Lawrence Krauss and others called it the greatest discovery perhaps of all time. And it was phenomenal. Stephen Hawking, who would give a seminar about this, touting this as evidence for one of his many theories. Of course, one of the safest things I've learned to do in life would be to bet Stephen Hawking, because he always would concede bets for some reason. So anyway, it's too bad I never got to make a bet with him. But there was always a nagging concern in all of our minds. And that was the signal all we thought it was? Or was it actually less than what we thought it was? Could there have been an imposter signal lurking about? So here's a wonderful cartoon from Sidney Harris. Does great work. So here are two women. They're cleaning up or doing something with a mop, and they're looking out how wonderful it is. And I'm reminded again of this guest, Neil deGrasse Tyson, on my show a couple of weeks ago. And he says things like, the cosmos fills us with conflicting emotions. On the one hand, we have this enormous capability to understand the universe. On the other hand, it's vast and enormous, and we're insignificant compared to it. So how do we reconcile it? Well, I think like dust is the connective tissue that links our mental processes, our ability to comprehend the universe, with the grandest things in the universe, but also the most humble things in the universe. Because indeed, the signal that we saw did turn out within a span of 6 months to be dust. And it's surprising to me how often I encounter somebody who says, oh, your book, it's about the bicep discovery that you guys discovered inflation. And I'm always, filled with some degree of pride, but also perplexed, because they'll know about inflation, but they won't know that we retracted those discoveries. And it's, I think, a byproduct of what I call the media science hype complex, not the industrial military complex, but instead that we make discoveries and they appear here on the front page. And then if they're ever retracted, they might be retracted on page, B17 of the Saturday edition, not on the Tuesday, Science Tuesday section of the New York Times. It won't appear there. And so my goal is to, maybe make this more awareness for our people when we talk about scientific ethics and production of things. It's not like we did anything unethical. In fact, the signal is more accurately known than ever. We measured a signal that's at the 1 part in a billion of the background. It just turned out to have a different interpretation. We didn't make a blunder. We didn't leave the lens cap on the telescope. We didn't have my thumb on it over the frame. No, we measured exquisitely a pattern of dust, and we were able to set a limit on how much inflationary energy density could be present in the early universe. Needless to say, my Nobel ambitions were blown away. And then just a few months after retraction of these claims came a letter in the mail from me from the Nobel Committee for Physics. So this is what it looked like. Now I ask you, all of you out there, even on YouTube, do not screen share this. Do not share. This is strictly confidential, everybody. This came from the Nobel Committee for Physics. And even though I reprinted it in my book, please do not share. But it says, they're asking me to nominate the winners of the Nobel Prize that perhaps my team and I, maybe me, could have been eligible to win. So it'd be like, you guys invite me to give a colloquium. I say, Christian, I'd love to give a colloquium, but could you actually put me in touch with, I don't know, who's your arch rival over there in Towson? Who's your bitter nemesis, Christian? Anyway, it'd be like that. It felt a lot like that. And so the question that I studied as an academic, I said, let me take this seriously. Let me ask the question, what is this letter asking me to do? It says, work done long ago may be selected for the award only on the supposition that its significance has until recently not been fully appreciated. And it also said, there was a message down below. It said candidate and then S in parentheses. That was kind of interesting. So I said, well, let me be a good academic. Let me go back to the original source material like I teach my undergraduates. Let me go to Alfred Nobel's original last will and testament. Here it is. And I speak fluent Swedish, so it's easy for me to translate. No, I don't. But I actually can find translations of it. Although the translations keep changing, they do actually change the wording of his will, which is kind of weird. I know I wouldn't want that, but this is what Alfred originally said. He said, the whole of my estate shall annually be distributed in the form of prizes to those who during the last year, the preceding year, shall have conferred the greatest benefit to mankind, apportioned as follows: 1 part to the person in the singular. So there's 3 conditions I divined. 1, it should be given out to the person the preceding year. 2, that person shall have made the greatest contribution or benefit to mankind through their discovery. And 2, it should be a single person. So I went back, let's see this again. Work done long ago. Well, that doesn't sound like last year. And that's significance, still not last year. And candidates, plural, that violates the stipulation against a single person. That's weird. Maybe the greatest benefit to mankind. No, that doesn't appear at all. So I started to get a little bit troubled, and I went back in the history of the Nobel Prize, as I think a scholar should do. And I took it seriously, and I asked, which of the following inventions won the Nobel Prize? And usually if I had more time, I'd ask you guys to take a poll here, as I do with my students. So all these were invented after Alfred Nobel died and or were eligible. In other words, their inventors were eligible to win it during his lifetime, and yet only one won it. And of course, it's not the periodic table, of which element number 102, symbol NO, that stands for nobelium, that did not win the Nobel Prize. Neither did the discovery of the RNA molecule, the precursor to DNA. That didn't win the Nobel Prize, but the lighthouse did. And that was invented by Swedish inventor Gustav Dalén 7 years after relativity was conceived of by a guy named Albert Einstein. And he didn't win for another 9 years after this invention. So it's quite startling who has won it and who has not. Here are some winners who have won it to great controversy. Here are some people that have been nominated recently. We won't talk much about that. Here's an abuse scandal that actually shuttered the Nobel Prize in literature. And I started to think, well, there are other kinds of problems with the Nobel Prize. For example, I work at UC San Diego. We have our physics department is named after one of the 2 women prior to 2018 to win the Nobel Prize in physics. Her name is Maria Gephardt-Mayer. So this is the sum total of women who had won the Nobel Prize in physics. One in 1903 and one 60 years later, Maria Gephardt-Mayer, who was a professor here. And even when she won, the prize was sort of tinged with a little bit of strange sexism in that. And this is something her son told me before he passed away in 2012 when the stamp was dedicated to her. And that was that when the headline in the Evening Tribune, which is what the San Diego Union Tribune used to be called, here was the headline: San Diego mother wins Nobel Physics Prize. So that's kind of funny, right? I mean, they were so sexist back then. That would never happen nowadays. Well, fast forward to 2018, when the wife of my late colleague, Andrew Lang, who makes a huge appearance in Losing the Nobel Prize, tragically committed suicide, as you'll find out if you read the book. Anyway, she won the Nobel Prize. And here's the headline at JPL: Caltech mom wins Nobel Prize. Son is JPL Mars flight technician. So, 50 years later, they're still doing this. And so I started a new website, maybe to start some change. I let it go after a couple of years of running it because we led to such great success in losing the Nobel Prize and getting more attention to women that just since my book, and probably only because of my book, we've doubled the number of prize winners by women. No, I'm just kidding. I had nothing to do with it. But it is interesting that we've doubled just since my book was written. So progress is being made. Still a lot. You'd have to give a Nobel Prize to women every year for the next 100 years to make the number of women and men equal. That's just a factoid. But the question became, why is the Nobel Prize so worshipped by people that even when a Nobel Prize winner, such as Duncan Haldane, shown here, he comes to UCSD, he brings his Nobel Prize with him, and then people gather around that are physicists, gather around and worship it. I found that embarrassing on behalf of my fellow physicists. So embarrassing that I then posed with it, and I'm a guy who wrote a book about the Nobel Prize. And I don't have any problem with the guys that win it or the girls that women that win it. But it's something in our culture, in our society, that makes us want to win these awards, and sort of it testifies to our abilities as human beings when we realize that it's actually just people like you and me who are responsible for making these awards. It kind of maybe dilutes some of the worship that we have of it, but I'm not sure that it will change. In fact, here's the Fields Medal. It was stolen just minutes after it was given, and it's given to this young man in Coucher Birkin, and after this was awarded, it was given away. And this is an award, that's in some sense called the Nobel Prize of Mathematics. In fact, it's described there in the New York Times, and it was stolen. And unfortunately for him, I don't know if he ever got it back, but they could probably give it to him. It comes with a 1.5. It comes with 15,000 Canadian dollars. And that's nice, but it doesn't compare to the million plus that you get if you win the Nobel Prize by itself. But anyway, it gave me an idea for my next book, which is going to be called Stealing the Fields Medal. So that's my next book. No, and that's not going to be my next book. Is the dialogue, and actually I'm doing another book about what lessons you can learn from Nobel Prize winners to emulate them, because I do think their minds are worthy of emulation, even if the process itself has these deep flaws within it. So the question is, where do we go from here? And this is where I say dust is the most interesting substance in the universe. As Gandhi said, if you're seeking after truth, you should be humbler than the dust. The world crushes dust under its feet, but the seeker after truth should so humble himself that even the dust could crush him. Only then, and not until then, will we have a glimpse of truth. And this is from his book, The Experiments with Truth. And I like that because I'm an experimental cosmologist. So pardon our dust. Now I'm going to talk a little bit about an upcoming experiment to extend the results of the BICEP experiment, which is now in its 4th generation, called the BICEP Array. And we have created a new experiment called the Simons Observatory, which is directed by me and spokespersoned by Suzanne Staggs up the road at Princeton. And we're a collaboration of over 200 people now. And here's a team shown at our last face-to-face meeting almost 2 years ago. Hard to believe. We hope to be back face-to-face this summer, in person in New York City, maybe socially distanced. Many of us have vaccines. So that'll be something for me to look forward to after a 2-year hiatus. And it's sponsored by generous grants from the Simons Foundation, the Heising Simons Foundation, and our 40 member institutions who contribute financially, in cash, in kind, and through their service and dedication to the project. So what is the Simons Observatory? How is it going to go beyond what BICEP was able to do and overcome the challenges that it has with regard to dust? It's a very simple concept. To get rid of dust, what do you use here on Earth? You use a vacuum cleaner. So we have commissioned to build an enormous space vacuum cleaner that will actually suck up all the dust in the Milky Way galaxy. This is no, we're not going to do this, but it's surprising how many people think this would be a cool idea. Actually, I think it would be a cool idea. We're just now getting, from Hayabusa and other experiments, we're getting samples of cosmic dust, which is not so dissimilar from these objects here, which I give away often if you join my mailing list at briankeating.com. These are meteorites. Asteroids are just giant chunks of dust. These things in the vacuum cleaner and the space sucker, those things are just microscopic silicates. Sometimes they have iron in them. The iron allows them to get aligned in the magnetic field of the Milky Way galaxy, and that can mimic the signals that we're looking for. No, we're not doing a space sucker. We're doing a microwave telescope system outfitted with 4 telescopes, 40,000 detectors. So we're talking about 40 times the amount of detectors as the BICEP 2 experiment. And these experiments will be comprised of an enormous reflecting telescope, 6 meters in diameter. So we're talking now 12 times the diameter of BICEP 2. But then we're also using BICEP 2 style telescopes, except we're supersizing them and we're photocopying them, and we're making more than one. So we're making 3 detectors, cameras. Each one is similar in concept to BICEP 2 in that it's a refracting telescope on its own alt-azimuth. That can also spin around. It's protected inside these ground shields. And the detector array system has, as I said, many more, 40 times more detectors than BICEP 2. Each one of these 3, and then there's 3 of them. So you're talking hundreds of times more detectors. And each detector is more sensitive, and each detector will have sensitivity to multiple frequencies. And that's what allows us to eliminate, we hope, the pernicious effects of dust contamination in the cosmic signals we seek. Here's an image of it in my lab, which I can literally see across the street from me, where I am now at the Physics High Bay at UC San Diego. I hope your most talented and brilliant undergraduates will please apply here next year. Application deadline for graduate school is December 15th. That will come up surprisingly fast in my estimation and in my experience. Don't let that happen. Ask your professors like Christian to write you letters of recommendation. Get those in early, so that you may join us in this voyage to 17,200 feet, more than almost twice the elevation above sea level as BICEP was at the South Pole. This is now in Chile. We've now actually broken ground on this site, as you'll see in just a second. Just last month, we've made tremendous progress, as this image shows here. Whoops, let me close that out. Sorry about that. I want to delete this picture here. Showing too many things here. Christian, can you still see last month, it says? And there are people pouring concrete?
Yeah, we do see that.
All right, so we're pouring concrete at 17,000 feet. In the summer, it's snowing at this site in Chile. It's a very challenging environment. We're pouring 3 of the circular pads that will hold these 3 small aperture telescopes, these refracting telescopes. The refracting telescopes will get, instead of 0.25 degrees above absolute zero, it'll actually get twice as cold as that. It'll get down to below 0.125 Kelvin. So just 100 milledegrees above absolute zero. This is a very challenging environment to work. You see everyone's wearing oxygen. They're also wearing face masks because COVID has resurged down there. This is big science. It's extremely challenging, but it's so much fun because not only do you get to do work with some of the most brilliant people in the world, you get to build this basically from scratch. And it's very rare. You can't build the James Webb telescope from scratch anymore. And you can't kind of be like an astronaut with oxygen on your back, going up and doing all this, and do it from actually building the detectors and instrumentation and then taking them all the way through to analysis. This is what a cosmic photon will see about a microsecond before it ends its 14 billion year long journey to our telescopes. Those are the 3 pads, the circular ones. We cover them up with tents to help the concrete cure. This is taken from a drone, which we will use the drone to do calibration. So we'll shine a perfectly calibrated signal into the telescopes to make sure that we can understand the signals and separate the dust signal, for example, from the cosmic signals that we're seeking from the quantum origin potentially of the universe. And so we cover them with this a tent material there, and that's what you're seeing in the previous slide. So that helps the concrete cure, keeps it warm. And these are all things you never think an astronomer would have to think about, but it's really fun. And it's just amazing to build this huge facility. You can see places where we're building buildings. You can see an excavator there. and you can see a large circular pad in the upper right. That's where the 6-meter telescope is going to go. And then there's a huge cliff there that falls off and goes down to about 9,000 feet. So be careful if you're up there. So this is a wonderful thing. I hope people will join us in getting to know this instrument and getting to know the science that we're doing. I think it's some of the most interesting science that we can do. I'm so excited to share it with you. And I will now leave you with our beautiful animated logo, Simon's Observatory, and quick image about my book, which you can find anywhere books are sold and or bought. And then a last opportunity to implore you to visit my YouTube channel. If you're on Christian's channel, he'll be on my podcast in a few weeks. Please check there. I had Michio Kaku on this week talking about the God equation. I've had on other thinkers like Neil deGrasse Tyson, 9 Nobel Prize winners, etc. And if you want a quick link to it, you can just use your camera, whip out the camera, and take a picture of either one of these icons, and you'll get more information. So I want to thank everybody, and especially Christian, for being such a great host and friend of mine. And I hope we can only meet at some point in the future.
Oh, well, likewise, and thank you so much, Dr. Keating, for coming out and talking with us today. I'm just fiddling around here with Zooms as I try to remember how to make this thing actually work once again.
Okay.
Let's see. So, yeah, I had you spotlighted, and I'll probably figure it out while we're chatting. But anyway, I do want to thank everybody for, well, first of all, again, thank you, Dr. Keating. I do want to just quickly see if there are any questions. We have several questions coming in from YouTube, and I just want to see, first of all, anybody here in our department have any questions for Brian? So, Brian, one thing I was, okay, I think... is anybody keying up? No? Brian, one thing I was a little bit curious about is you were talking about the bicep result, and obviously that was obscured due to dust. And I probably missed what you were saying because I was looking at some of the comments coming on YouTube. But this the new observatory you're working on, how do you mitigate against dust in this case? It sounds like the trick is somewhere in using the 3 instruments across multiple wavelengths. Did I understand that correctly?
Yeah. So in order to get rid of a cosmic signal, what you have to do is have another experiment, and the other experiment then allows you to measure the unwanted signal. And by measuring the unwanted signal and the desired signal in combination, and then something that only measures the unwanted signal, which is brighter than the desired signal, then you can subtract the unwanted signal from the desired signal. So to do that, my brilliant colleagues, Suzanne Staggs and Adrian Lee, and their teams, both at NIST in Boulder and Berkeley and Princeton University, they have devised multi-chroic, simultaneously detecting multiple frequencies and multicolors. And you can see how the ones on the right work maybe a little bit easier than the ones on the left. The ones on the right, there are these kind of like spiral pattern, fractal pattern. And so if you're a CMB photon, this is what you see right before, about a nanosecond before you end your billions of year long journey. And then depending on what your frequency is, you'll resonate at a particular lobe, a bulbous lobe on one of these antenna structures. And so at the very smallest structures, those are the highest frequency. That's where dust is brightest. Dust peaks at high frequencies at hundreds of gigahertz, say 300 gigahertz or so. And so we have frequency sensitivity simultaneously from where the cosmic background peaks, where the inflation signals might lurk. That's about 100 gigahertz. And then we're simultaneously measuring at 200 and 300 gigahertz as well to mitigate the effects of dust.
Okay.
And then to mitigate other effects, we can also measure at lower frequencies, and that's what those really giant lobes are in the pixels that are shown here. And so that's the way that we're doing it, simultaneously measuring the desired signal, the dust comes along for the ride, and then you subtract the dust-only signal from the CMB plus dust signal. That's a good question.
Okay, great. Thank you. And let's see. I know there's a couple other questions coming in from YouTube. I am just taking a quick look at these as I'm talking with you, Brian. Let's see. One of these is, well, this may be a little bit you may have already spoken about this. Some of these questions came in earlier in your talk, Brian. But LV Gamer on YouTube, LV Gamer Cats on YouTube asked, how exactly do you measure the polarization of the CMBR?
So the polarization of the CMBR, of the cosmic microwave background radiation, is like any radiation. It has three properties. It has a color, it has an intensity, and it has a polarization. Now, most light is unpolarized. And so to measure polarization, you need something that separates out the degree of polarized light from the degree of unpolarized light. Typically, you do that with polarized sunglasses. I don't have my polarized sunglasses here, but I do have some polarized film that I keep on hand for occasions just like this. And if you'll bear with me, I'll find it. But you've all used polarized sunglasses. And the way that they work is they admit one polarization state preferentially compared to another. So actually these cameras are polarized slightly, and actually the reflection is polarized. So I can twist this and the intensity will get brighter or dimmer depending on what polarization. It's hard to do it. There it is. So it's hard to do it. So it will get brighter or dimmer depending on what polarization the light is emitted with. And if it's unpolarized, then rotating this polarizer won't do anything. So if you're outside and you have polarized sunglasses and the sun is out, look 90 degrees away from the sun, look at a right angle. If the sun's over there, look straight up. At sunset is a good time to do this. And then rotate with your polarized sunglasses and you'll see a bright, dark pattern emerge. And that's because light gets polarized in the Earth's atmosphere upon scattering. Our detectors shown here, actually the ones on the left that are shown on the screen, have this plus or cross-like pattern on them. So they separate out a polarized vertical polarization signal. The ones that look like pluses, they can detect horizontal and vertical polarization, because that's where the light or the microwave radio frequency energy will radiate and resonate, and then we'll detect that using what are called bolometers. And then the ones that are at 45 degrees to that, they measure the orthogonal components to those vertical and horizontal. And the combination of all four of those patterns can allow us to reconstruct the polarization of any light pattern, and in particular, the cosmic microwave background polarization. So polarization requires two things: some ability to separate out polarization into different components. And by the way, light can be circularly polarized or it could be linearly polarized. And by doing that, you separate it out into circular or linear, and then once you have it separated out into horizontal or vertical, or left and right, and then you have a detector for each polarization state. So there's 4 detectors shown in each one of these spatial pixels. And then you do that for each frequency. So there can actually be 8 different individual detectors for the 2 different polarization states times the 2 different frequencies per spatial pixel, times the 2 different orientations. So there's actually 8 different detectors. It's quite astounding what my colleagues are doing nowadays in detectors.
Well, thank you, Brian. And actually, that dovetails. I believe you mentioned about who was people work on this. A memory thief was asking who makes that detector. So is that being hand built at one of the universities, or is it a contractor? How do you actually go about building these things?
Yeah, so they're previously they were really built a lot by our graduate students at Princeton University and at Berkeley and San Diego. We actually merged these 2 competing experiments, one led by Princeton and Penn called the Colloquium Cosmology Telescope. And they built technology like the one on the left with the gold-plated it looks like little sockets. And those are actually horns. Remember the giant 6-meter horn antenna at Holmdel, New Jersey, used to detect the CMB the first time? That was a single pixel. That was a single horn that channeled energy down to a superconducting receiver called a mixer. At any case, that detector, we're making 10,000 of those in a single receiver, and each one is 1 billion times more sensitive than the Holmdel detector that Penzias and Wilson used. So it's just astounding. The process is faster than Moore's law in terms of sensitivity and in terms of number of detectors per year, how fast we're doubling the number of detectors and the sensitivity of each detector per year. It's faster than Gordon Moore's law would predict.
Fantastic. And we do have another one here. I'm probably not going to get a chance to get to all these questions today, and I appreciate so many of them, but I'll go ahead and bring this one up here. Guy Manuel asks, do we then have a representation of what it might have looked like at the moment? And he's referring to the CBR. I'm only curious because otherwise CBR is fascinating as it is. So I hope, Guy, I'm understanding your question, but I think you're trying to ask, do we have an understanding of what the cosmic background radiation looks like today, given that it's been traveling for so long? I hope I'm interpreting your question
Um,
correctly.
yeah, I mean so light travels not unimpeded. Light can be affected by everything it encounters along the way. So I showed this early on. The oldest light in the universe is this, kind of rainbow pattern, which is called the CMB, is a relic. It's a fossil. Photons are fossils, and they live forever, we think. And they've been traveling since the origin of light itself in this form. In other words, light existed at the Big Bang, shown here at t=0, but it got scrambled and jumbled up by interactions and scattering with all the protons and the plasma that was existing in the primordial soup until the universe expanded enough and cooled sufficiently to form molecular or atomic hydrogen, which is a proton and an electron bound together is electrically neutral. And then there's no more plasma. And then those light particles, those photons, can travel unimpeded in any direction unless they're absorbed by some matter, some telescope or some planet. And the universe is surprisingly sparse. Look at the Hubble Deep Field image shown there. Most of that image is dark. In other words, most of the universe is actually a pretty dim place. It's poorly lit. And that means there's very little ordinary matter. Dark matter doesn't interact with light, it can't absorb the CMB electromagnetically. That's why we call it dark matter. So that light can travel from the rainbow pattern all the way to our telescopes today. And it utterly misses even, all these massive planets in our solar system are utterly insignificant. And so, yes, we can see it as a pristine fossil relic. Like, we are space archaeologists. Looking back in space is looking back in time. And that allows us to study the infant universe, at least as long as there was light that we could study currently. And now the question is, can we study what happened earlier in the universe? Can we study a phenomenon that doesn't produce light and instead produce waves of gravity? And that's the so-called B-mode polarization that we hope to do. And that we do by looking at the imprint of waves of gravity on the CMB itself. And I should say that Christian and I should probably spend more time discussing this in the future, because it is a very rich subject. But I hope the book also gives a good overview of the physics behind it, of polarization, and how the universe is actually an observable place that we hope to be able to reveal what happened. Maybe not at time=0, but maybe as early as humanly possible to reveal.
I think we can definitely make that happen, Brian. We should definitely have you back on the show. Let me see if I could switch back over to this, and I'm going to try to, let's see, I think you have to stop sharing your screen. Let me make sure that there aren't any other questions coming from inside our department. Thank you, Brian. And yeah, okay, great. So I think I've got, Brian spotlighted here. But anyway, I'm up here in the upper corner. Hi, everybody. So I want to thank our guest once again, Dr. Brian Keating. That was a wonderful and fascinating talk, Brian. Thank you so much, man. And and we'd love to have you back, either for another colloquium or for. Why is this thing good? I'll love you back for another colloquium, and for those of you watching on YouTube, I hope you. My apologies for not having as smooth a production as I normally enjoy, because I've been using Zoom. We're doing this, and just kind of toward the end thought, hey, why not live stream it? So this was a lot of fun. And by the way, speaking of live streams, at the risk of shamelessly plugging, we do have our planetarium show, our live stream, which will be tonight at 8 p.m. Eastern Time, in lieu of the lack of ability to actually present a planetarium show. We're doing them online. So we're going to be having another guest on tonight, Dr. Michael Brotherton, who we'll be talking about quasars with. And these are next to the cosmic microwave background that Dr. Keating studies. Quasars are the second most distant objects that we can probe into the universe. So it should be a really fun and exciting discussion. I invite you to come and join Dr. Brotherton and myself tonight on this channel on YouTube at 8 o'clock Eastern Time. But we haven't seen the last of our friend Dr. Keating either. We're going to have him back on shortly to talk some more about this as well. So thank you all so much for joining us today. And as always, stay healthy and stay curious, my friends. Talk to you later.